I'm very happy to be here. Thank you for the invitation. I'm going to be talking about a system that we've now seen there are many challenges, but we've been trying to create a communication system that has some highly secure properties. So more particularly, we've been working on a system called Scion. I'm sorry for some of the fonts look a bit different here. I did not write my name this large. But in any event, so we've been trying to create a communication system that has highly secure, prevents highly secure communication and prevents many of the attacks we know today. So we all know about the internet, and we know there's a lot of issues. Besides the security aspects, there are three particular issues that we want to address. This is loud enough, by the way. I don't want to yell into this. So first of all, today in the internet we can only use a single path. Right? So we send a packet, the packet traverses the internet in some way. We don't really know how. We cannot really pick. And that's a problem because this one path that the packet goes is oftentimes not the best path. Right? So some packets we'd like to have low latency, some we'd like to have high bandwidth, but we cannot really pick which one this particular packet should take. Another problem is there's a lot of outages. The BGP protocol has many issues. I could talk for an hour about all the ways in which you can misuse BGP to actually attack the internet, to do a kill switch, prevent people from communication. Also, from a privacy perspective, BGP has been misused to attract packets and then eavesdrop on those packets. So we've seen state actors redirecting internet communication using this BGP protocol in order to then eavesdrop and record the traffic. So that's a lot of issues in that sense. And there's also a lot of ambiguity with how the internet behaves, a lack of transparency. We'd like to have much better transparency into the internet. What is it actually happening? Whom do we need to rely upon? And so on. Lots of issues here. So the vision that we've been pursuing is to create a global public internet that provides high security. So it's not a private internet or like an SD-WAN where you have a few sites that you want to connect with each other. This is really a public internet connection. So you purchase one internet access, a Scion internet connection, and what you're getting is highly secure communication to whomever else has a Scion internet connection. So that's really the important aspect of the vision here. Achieving high security availability, path-aware networking to be able to control where packets are going, and also multipath communication so you can use many paths simultaneously, which helps with availability, DDoS defense, but also a bit with privacy. So I don't have much time. I apologize, the colors look a bit different. But here's a high-level overview of the Scion architecture. This is really a global internet architecture. So this is not a local, SDN or some local system. This is really for addressing global routing. And one of the main aspects is that it's path-aware, which means the network path is going to be embedded and is known what it is when you send out the packet. So like every network architecture, we have what's called a control plane. This is a mechanism to find paths in the internet, how packets should route, and also a data plane when you actually send the packet to then deliver the packet to the destination. So to find paths, we have a mechanism that essentially finds path segments. So it's not, we don't identify, like in today's internet where every destination sends out a message to the whole world, we have a different mechanism where we just find these segments, and it's a hierarchical mechanism. So we have two levels of this path finding to make the system very efficient and scalable. So we first find segments across large areas of the internet. You can imagine like the superhighways or the highways to find paths that get you very far at high speed. And that's shown, you can see these isolation domains. These are these colorful ellipsoids. And these smaller circles are representing autonomous systems. So these are domains like ETH or Swisscom or any entity will be the smaller autonomous system. That's the smaller circle. And so you can see from here, it's a hierarchical mechanism where we find first paths across isolation domains, what we call these bigger bubbles, and then also paths within each isolation domain. So you can imagine paths that bring you to the highway, local paths, and then a path on the highway to get you close to the destination, then again a path towards the destination on the local path. So the system identifies these paths, distributes them, and then in the, apologize, there's some issues with the animation hour. What you can see is the packet when you send it, then these path segments are being encoded in this packet here. There's also several cryptographic layers to protect the security on the way to find these path segments, to how they're disseminated, they're also protected. And also in the packet, they're protected in a way that nobody can change them. So with very efficient cryptography, that can be verified within a few nanoseconds when the packet is being sent. So a highly efficient system and secure. We actually claim that we can achieve even higher speeds than in today's internet. I can explain this if time permitting. But then the packet will really go along these path segments, source to destination. This gives this transparency. It even enables simpler routers, so that the routers don't need very large routing tables anymore, which surprisingly is actually an issue in today's internet. All right, so Rufa was saying, well, you got to speak a bit more about privacy. So I added this slide here. And there's a lot to be said about privacy. We've actually, a few years ago, we implemented a system called Hornet, which was an extension to Scion for providing very high speed privacy, a system similar to Tor, but running at a speed of about 1,000 times of what Tor delivers today. So, but here, because we have limited resources, we decided to wait with these anonymous communication systems. And so currently we're pushing mainly the whole system to design and implement the basic communication system. And then once it's in place, we can go back to again work on anonymous communication. However, even today, Scion offers several ways to support privacy. And the first way is sovereignty. So in Scion, the different isolation domains all select their own roots of trust. And so you can exactly see whom you need to trust for any operation. So it's very transparent also in that sense, that the roots of trust that need to be relied upon are well known and are very well visible. And this enables also local root keys, so not that the whole world has to trust some key that the whole world, or a key that only a few entities possess. It's really, you can set up isolation domains and define the keys that you need to trust for communication inside that isolation domain. Also, there's actually many kill switches in today's internet, ways to turn off communication in parts of the world. And this also was an explicit way that we built into Scion to prevent to be able to communicate. And this, for instance, also can support privacy. One could, for instance, use a kill switch to prevent communication unless it goes through certain points that it can be eavesdropped on. So then it can help in that way. Turns out hijacking attacks, route hijacks, are today also used to eavesdrop as well. So one can, if they're not on the path, use a BGP hijack attack to reroute communication to go through points that they actually control. And there were some reports last year that showed that some ISPs are actually doing this on the internet today. They're actively rerouting traffic to then eavesdrop it. Because in Scion we prevent these type of rerouting attacks, one can then not change the path of packets. So if you know a certain path is safe, you can use it, cryptographically protect it in a way that it cannot be altered. Path transparency, you actually know the AS level paths. If you know somebody's eavesdropping in your traffic, it would not.
We're actually we're getting hacked live.
Right. This is
on the computer.
This is not my computer, so.
Yeah, I know. By the way, I have 16 gig of RAM, so even if there's a lot of malware, it should keep one functioning.
I'm pretty relaxed here, seeing.
It's public information.
So. Also, multipath communication can actually help with privacy because you can send packets in different ways. And now if somebody wants to eavesdrop, they may not see all the packets that you've sent. They may only see a partial pattern, and it becomes much harder to also correlate and reconstruct the communication. Definitely at large scale, multipath communication can help quite a bit. Also, we've been talking about how can we actually verify the systems. And so at ETH, we have an effort called Verified Sign-On, and I'm happy to say that two of the PhD students working on that are back in the room who know a lot more about this. I mean, it's the teams of Professor Bazin and Müller who are working on the formal verification of the whole sign environment. The goal is to achieve communication that has provably strong security properties. So here's how this works at a very high level. There is a protocol description, and again, the student Tobias here actually is exactly working on this problem to use refinement techniques in order to verify to verify the protocols at that level. And again, I apologize for all the font issues. So through these refinement techniques, you can start with a very simple system that is incomplete, but make it more and more concrete and more sophisticated. And at every step, you prove that you preserve some properties. And in the end, you can show that the end protocol actually has the security properties you seek. Then there is sorry, this is really hard. There's a router specification, and it looks quite different here, but so router specification, and the team shows an equivalence between the protocols that have been proven and this router specification. So at this point now, you know that your protocols are actually secure, that with respect to a certain attacker model, and that your specification for the router that you built is also satisfies these protocols. And now another hard problem is to actually then show through formal verification that the implementation now also satisfies this router specification. And so Professor Bazin's team works on verifying the security protocols, and Professor Müller's team focuses on verifying the code executing on the router. So the property, for instance, that you can verify is that there's no backdoor freedoms at the scale of internet router. And so this is quite interesting that we can actually do this on real systems. So we've been working on this project for over 10 years, and there's already quite a bit of deployment underway. We've been having a production network with customers using it for actual production traffic since 2017, and successfully so. And so we also expect that 3 ISPs are going to have an official offering of selling a SIGN connection this year. So you can call them up and say, I'd like to buy a SIGN internet connection. We're currently also setting up connections with ISPs around the world, particularly in Korea. We're currently deploying, so you can buy a secure SIGN connection in Korea, one here in Switzerland. You can already have highly secure communication all the way that's completely independent from BGP and completely independent from any of those events.